I can see the cylinder.
There we have it. Now I'm going to try to explain partial pressure just for a little bit. Think of this cylinder as being filled with water, because most of what we're dealing with is partial pressure of water. And of course, the blood is mostly water, so blood's partial pressure is not exactly the same, but it's close to that of water. We won't go into it, but let me tell you, you can, if you really get into study of the breathing and so forth in your lungs, partial pressure is real important to the transfer of carbon dioxide as you breathe out, oxygen, O2 that you breathe in. They're both real important. And we breathe in not only carbon dioxide, but we put other gases into our lungs, into our bloodstream as well, to our lungs. But what we have here is, think of this in the bottom portion where my mouse is moving around of the cylinder is filled with water. And above it up here is air, right? Now the air, the water molecules, and inside the water, mixed with the water, will be gases. Some gases can go into the water itself. Carbon dioxide, oxygen, and nitrogen can go into the water. And what happens is, when the water begins to warm up, as the water, if it's real, absolute zero cold, there's no molecular movement at all in those water molecules. As it begins to warm up a little bit, and I'm going to raise my mouse up to indicate the temperature is coming up, as that happens, the molecules begin to move around, get some kinetic energy, they move. And at some point, a few of them will get enough energy to fly out of the ice, and then they'll go on out, and that's called sublimation. We also would get a situation where even if it's liquid water, there'll be more of them that get energy. There'll be more of them moving around. And when they're frozen, they're not moving as much as when they're liquid. And so as we warm it up, past the point of melting the ice, it gets moving faster and faster. More of these air molecules, that will be oxygen, nitrogen, carbon dioxide, and so forth, they'll get enough energy, one molecule at a time will get enough energy to fly out of the top of it and become part of the air up above. Now, we also have a situation where we're pushing them down into it from the above. And so some of them get enough energy to drive themselves down into the water, and they impregnate in the water. So they become part of the water. So I'm just trying to simply explain this as simple as I can. Now, what happens, there's a point of equilibrium where those coming out and those going in are equal. So we get a constant amount for a given temperature. There'll be a constant amount of oxygen that can get into the water and carbon dioxide that can be in the water, or other gases like nitrogen. Is that pretty clear? You heat it up more, and more of these gases will come out of the water and fly up into the air. And so you'll have less, as it warms up, these gases will come out and there'll be less of them in the water. I would suggest that you do this as an experiment tonight. Put a pan of water on a stove and start warming it up and watch. You'll see air bubbles coming out of the top of that water, out of the side, particularly if you get a glass container, like a plexiglass or something that you can heat up without damaging. Don't get a glass that can't stand heat. Something that you can cook out of, you see the side of it. You can actually see the air molecules coming out of the water, and they'll be coming out of it. And that happens. And so that water gets less and less air in it. It's more just H2O. Are there questions? So lakes, as it warms up, they'll have less oxygen in the lake. All right. Now, then that was from last week's lesson. This is lesson 18 now. And we were studying the biblical flood from out of my flood book, second edition of the flood book, which is not yet in print. We're going to look at the canopy and radiocarbon dating. Carbon normally, most carbon atoms have 6 protons and 6 neutrons in the nucleus. And they will have, if they're not ionized, they'll have 6 electrons. So it'll be 6, and that will be number 6. And then it would be in here, instead of a 6 right here, let's go back. We would have a 6, and then we'd have a 12 up here normally. And but we have a carbon that's got 14. We're going to talk about it just a bit. It's called carbon 14 or radiocarbon. It's radioactive. It decays. And it's produced by several different mechanisms, mostly by cosmic radiation. We'll talk about how it's produced here in just a few minutes. Questions so far? Most carbon-14 is produced by hydrogen neutrons coming from space. Majority come from the sun, but some from other stars. Remember, the sun is a star, okay? And most are coming from the sun, but there's some from other stars. A lesser amount is produced by protons coming from space, the sun, and other stars as well. So there's more than one mechanism to produce it. There are even some produced by lightning. Lightning bolts can produce some. Okay. Willard F. Libby, came up with radiocarbon dating, and he was born in 1908 and died in 1980. He came up with it in, I think it was 46 or 47, 48, somewhere thereabouts. And he got the Nobel Prize several years later for it. I think it's in our notes here. A smaller portion of radiocarbon is produced by other sources, such as lighting and even by the impact of meteors. They discovered that, and I've documented all of that. Atomic bomb testing in the atmosphere that began in the 1950s created a significant amount of radiocarbon and changed the amount of radiocarbon that we have in our atmosphere. I think it was a permanent change of situations, and radiocarbon is not good for us to have in our bodies. Period. It's bad for us. So keep that in mind. But atomic bombs did change it. So whenever they talk about the dating, they say before BP, before present, they mean before 1950. There are 3 main isotopes of carbon. As far as I know, that's the only isotopes that exist. They might be able to make some in nuclear reactions or some kind of a nuclear reactor of some sort, but I don't know of any others. There's carbon-12. Most of your carbon is in this form. 98.89% of it is in the form of this isotope. So it has 6 protons, 6 neutrons, and unless it's ionized, it'll have 6 electrons. That's your main stable. It's stable isotope. It does not decay radioactively. We have carbon-13. It's a small amount. About 1.11% is carbon-13. And it has 6 protons. That's what makes it carbon, but it has 7 neutrons. And it'll have 6 electrons unless it's ionized. And it's also stable. It's a stable isotope of carbon. But only about a little over 1% of the carbon is carbon-13, right? Carbon-14 is radioactive, and that's a very small amount, less than the 1/10 of 1/100th of 1% is carbon-14. Now, what this carbon is, it has 6 protons, and that's what makes it carbon, but it has 8 neutrons. So that gives you 6 plus 8 is 14 particles in its nucleus. It's unstable, it's radioactive, it decays over time. Now let's talk about how it's produced. Cosmic radiation, usually a neutron comes in and hits nitrogen. Now nitrogen normally has 7, most nitrogen atoms have 7 protons and 7 neutrons, okay? And so what happens is it captures that, let me get my mouse to move it, captures that neutron, and it then emits a proton. And so it lost a proton. Now remember, it had 7, it lost 1, that leaves it with 6 protons. So it had 7, normally it had 7 protons and 7 neutrons. But now it picked up another neutron and lost a proton. So what it has now, it has 6 protons, which makes it carbon, but it has 14 particles. It It has 8 protons now, see, because it started with 7, it gained this extra proton, it lost a neutron, lost a proton. So it has 6 neutrons, 8 neutrons and 6 protons, which makes it carbon-14. So that's how it turns into carbon-14. So a proton is emitted, it comes out, and of course it picks up an electron somewhere, it becomes a hydrogen atom. And questions so far about how that works. That's most of your cosmic radiation is a neutron producing this that produces carbon-14. Most of it's produced by that method, they think, pretty sure, okay, by neutron capture. So it becomes carbon-14. Then it goes down and becomes part of carbon dioxide, or gets absorbed by a tree or by some other plant. It can be then buried in the soil. It can be in the bones of animals. It can be in the fossils of animals. And what it's absorbed by some living organism. See, carbon-13 is rare, and radioactive carbon-14. All 3 of these are absorbed in the organisms, like trees and plants and so forth, in the bones of animals and so forth. Now, what happens is carbon-12 and carbon-13 don't change. They're not radioactive. But the carbon-14 decays over time, and it decays back, and it emits a beta particle, which is an electron. And what happens when it emits a beta particle, that turns back into nitrogen. So one of the beta particles is negative, so a neutron emits a negative, and it becomes positive. So it makes it into a proton. And now it's got 7 protons and 7 neutrons, and so now it's back to nitrogen. And it turns back into nitrogen. Now, that would be real bad news if that carbon atom happened to be part of your DNA. That would not be good, okay? Just thought I'd let you know that. So carbon-14 is not good for us. If it happens to wind up in your DNA, you may have a permanent mutation in all your offspring, your descendants, okay? But this horse here, or this tree, dies, and it gets buried, and then that carbon begins to decay over time. Okay. Any questions about how that operates? Okay. Now, it is produced by some other means, but most of it's produced by this means here. All right. Now, in the atmosphere, carbon-14 then goes with carbon with O2. Oxygen makes CO2. But it's a radioactive carbon in this CO2, and then it turns into nitrogen-14. The cosmic rays, neutrons, make it into this, and it goes into photosynthesis, into trees, into various trees and other things. It winds up also in the ocean as well. Through rainfall, it winds up in the ocean, so it'd be in the sea creatures as well. And so cosmic ray neutrons primarily do this. That's where it happens. Questions or comments?
Yes, I have one. Do they, this is Williams, do they normally stay at that number in the atmospheric mixing where you have carbon, neutrons, and dioxide?
No, it won't. Here's the thing. From a mathematics standpoint, there's a certain rate at which they're produced. And again, they assume the rate is constant, and they don't know that it is to begin with, first of all, but they've assumed it's a constant rate. And of course, exploding stars out away from us can produce a whole lot more over a short period of time. Supernovas and stuff like that can. But other things can produce it as well. Like I said, lightning and things like that can produce some. But if we assume they're constant, you have, let's just say that we have a hose going into a bucket of water. I'm going to illustrate it. And the hose is turned on pretty fast. And you put a tiny hole in the bottom of that bucket. Well, as the water gets deeper, you get more pressure, and so it'll come out faster out that hole. But what, at some point, if your bucket is deep enough, your hole is big enough, the amount of water coming in will equal the amount flowing out. Does that make sense? If you make the bucket deep enough, the container a bit deep enough.
Yes.
So depending on the size of your hole, you can get the flow in and the flow out equal. That's called equilibrium. And in that case, the amount of carbon-14 will be constant up in the atmosphere. It is not constant at this present time. Is that clear? And it should be constant within less than 100,000 years, or probably 50,000 years. What we're going to look at is this is a problem for the atheists, not for Christians. Okay? So right now, we're producing more than is decaying. All right? So we don't, it is still building up, and we're not at equilibrium. So the atheist, it should be at equilibrium if the Earth is more than 100,000 years old. It should be at equilibrium, but it's not. Okay? Any questions? That is a problem for atheists, not for Christians. All right? Here's the half-life. Now, half-life is something interesting. It says, let's say we had 10 pounds. In this case, let's say we have 16 pounds, okay? And this, I'll use the number 16. We have 16 pounds of this carbon-14. And so in this period of time here, we would come down, we'd have half of it left after this period of time right here, after this 5,730 years. Now, that's what they claim. However, they found that even that number that they've assumed is wrong. They've just found that is wrong. They made an assumption to get it, and their assumption they figured out was wrong. But they haven't corrected it. They've left all the data the way it was before. So they're claiming that 8 pounds would be left. If you started with 16, you'd have 8 left after 5,730 years, 5,730 years. And then of that 8 that's left, in another 5,730 years, you'd have 4 left. And then another 5,730 years, you'd have 2 left. And to go another 5,730 years, you'd have 1 left, and you'd have a half left, and so forth. Each time, each 5,730 years, half of it will decay and turn back into nitrogen. That's called half-life. Does that make sense? Any question there? Now, they claim this half-life is 5,730 years, but they've decided that's wrong and they have to have a correction for it. But they've done all this work before and they're not going to go back and undo it. But there's an error in that. They got an error in that as well. Right. The assumptions. The first assumption they make, did I answer your question, Freddie? Freddie?
Yes, sir. Yes, sir, you did.
Okay.
Thank you.
The first assumption is that the atmospheric level of radiocarbon was at equilibrium, which means that amount being produced is equal to that amount decaying at that time. So the decay rate and the production rate are the same, and it was constant. This assumption is now known to be false. It's known to be false. They assumed, they knew the decay rate, and they said, well, if we go a bunch of half-lives, shouldn't be any left. And so there should be, since we have a constant production rate and a logarithmic decay rate, exponential decay rate, then there should be a point at which they would equal each other, and that makes perfectly mathematically good sense, but they're not. And so they assumed they were because they assumed the Earth's billions of years old. They found out that assumption was wrong, which means something about the age of the Earth. They got a problem with the age of the Earth. This is a two-edged sword for them because it proves the Earth's atmosphere is young, less than 100,000 years old. At 100,000 years, it should have decayed down to virtually no radiocarbon in it, right? Less than that. I'm not saying it is 100,000 years. I'm saying it's less than 100,000 years. There's a difference. The second assumption is that the rate of decay of the radiocarbon atom is fixed and not affected by other factors. Now, that's an assumption that's made, and we'll talk about that later. Any questions? So we got two assumptions. The first one here is that it's at equilibrium, and that's known to be false. The second assumption, there is some evidence that this may be false as well, right? The third assumption is that the material has not been contaminated by other sources of radiocarbon. This would make it appear too young, right? Contamination is certainly a problem. And so that's a problem. We can't know if it was contaminated, right? Any questions so far about assumptions they're making? Fourth assumption is that no radiocarbon has been lost from the material to be dated. The third one was no extra radiocarbon came into it, and this one is none of it got out of it somehow. We could have the process of leaching from water. See, water could rain down through it, and water run down as it rained and leach some of it out. And there might be some unknown factors that would cause radiocarbon to be lost. There might be some other factors that would cause it to be lost. Any questions? 4 assumptions, and all 4 of them are pretty shaky. Since water vapor is lighter than nitrogen, most of the nitrogen would be confined to the lower atmosphere. Let's talk about the water vapor canopy now and talk about how it might produce radiocarbon. Since it's lighter than nitrogen, most of the nitrogen would be confined to the lower atmosphere, not in the upper atmosphere. High energy neutrons and protons from the sun would be stopped by the water vapor and would not collide with nitrogen atoms to create carbon-14. See? Because water vapor is lighter, it'll rise up above the nitrogen in the atmosphere. And so a thin, dense layer of water vapor in the upper atmosphere, the canopy, which I've postulated or theorized, would protect us from carbon-14 formation. Remember, I told you, if it gets in your DNA, it can mutate you. We'll give documentation for that a little bit later. This would mean that the antediluvian pre-flood atmosphere would have very little or perhaps even no radiocarbon in it. Virtually no radiocarbon, or very, very little amount of radiocarbon in it. All right. Such a water vapor canopy would shield the Earth from cosmic radiation, would make any accurate radiocarbon dating of fossils which lived prior to the flood impossible. If there was no radiocarbon, the dinosaur bones wouldn't have any in them. And so the fact that they don't have very much in them is within itself very telling. Of course, they use that to assume that they're very, very old. But if they didn't have it to start with, then they wouldn't have any in their fossilized state either, unless it got there by leaching or some other way. And make radiocarbon dating be unsound for the dating of things. And it would be unsound for anything prior to the flood. Okay. The waters above the firmament was a water vapor canopy. That's my postulation. I set forth that as my premise. The 4 days of rainfall dissipated the water vapor canopy and reduced the barometric pressure. Large amounts of oxygen were entrapped in the sedimentary rocks. And also carbon dioxide was too. Carbon in carbonate rocks contains no measurable radiocarbon, almost none, virtually no radiocarbon in them. Again, if there wasn't any before the flood, it was all deposited during the flood, there wouldn't be any in it. So that would explain that. The flood occurred around 3000 BC. We're going to get to that later, okay? These 5 facts prove that there was no radiocarbon in the antediluvian atmosphere. So I would argue, because we don't have any in the carbonate rocks and they were deposited during the flood, then there wouldn't be any in them. There wasn't any in the atmosphere. So our water vapor canopy would explain why this would be the case, okay? These facts are neither addressed to one who's an atheist. Now, I'm not addressing these facts to atheists. Why? Because they don't believe them, okay? Nor to an agnostic, but to those who believe the scriptures. Now, if you go back and you take the positions of the scriptures here, then you have to explain, if you're a believer in God, believer in the Bible, you have to say, well, why don't these carbonate rocks have radiocarbon? Well, because there was none before the flood. And that would, and our model would explain why there wasn't any there. Okay, so it would explain what we see for Christians, believers in the young earth and a universal flood. The following equation, mathematical equation, is used to date materials by radioactive dating, all kinds of radioactive dating, in this case, radiocarbon dating. So we have this basic formula, and I want you to notice here, N sub T, that's the number at some given time, is N sub O, that's the number of radiocarbon atoms at the beginning. E, and that's a base for natural logarithm, Euler's number, and this is negative lambda T. T is time. Now I'm going to identify these, what they are. N sub T is the amount of carbon-14 at the specimen being tested. They can measure that and then get that pretty accurately. So I don't question that. I'm not giving a much question to the accuracy of that number. Okay, N sub O is the amount of carbon-14 in the specimen when it lived. That's where they have their flaw. They don't even know what that is. They don't have any way of knowing. They just have to theorize what it is. They just have to guess it. They make an assumption that it's been in equilibrium for millions and billions of years, and that's not true. It's not even in equilibrium right now. Should be within 100,000 years, and it's not. So that's a problem for them. Lambda is the rate of decay of the carbon-14, and I've told you they've agreed that they don't even have that right. And of course, T is time. Now then, this other E over here, we're going to get back to it. The formula for radiocarbon dating, this formula here we just saw, has 4 variables, and only one of them is known with any precision. The amount of radiocarbon in the specimen, N sub O. Now, mathematically, we can solve the formula for T. We're not going to show it here, but we can solve the formula for T right here. And it's assumed that we know the rate of decay of the radiocarbon, that's lambda. This leaves us with 2 unknown variables. Now, I want you to see it. Here's your equation. Here's your measured radiocarbon. Here's your assumed amount of radiocarbon. Notice it's assumed. They don't know what it was. They're not back there 100,000 years or even a million years back or whatever to measure that. In fact, to try to measure anything but radiocarbon more than about 50,000 years is ludicrous because it can't do it. But so they can't go back 50,000 years and look at this and see how much was there. That's an assumption. Here's Euler's number. This is the base for natural logarithms. And it's a very important number in mathematics. And it's what's called an irrational number. You can't make it into a fraction of two whole numbers. There's lambda, negative lambda. It's a decaying, so it's decaying downward. That's why it's negative. And there's time. It's the rate of decay of the radiocarbon. Questions about the formula. You don't have to know much algebra to know if you've got an equation with two unknowns that you don't know, you only have one equation, you can't get a unique solution, you can't get one of a kind. You can get an infinite number of answers to it, depending on what assumptions you make. You have to assume what N sub O is in order to get what you have. So what they do, they know what they have, they think they've got the rate here, so they algebraically work this formula backwards for T, and then they plug in an assumed value of N sub O. So all based on assumptions, an assumed value. It's not good mathematics, okay? All right? Those using radiocarbon dating must assume how much radiocarbon was in the specimen when it was alive. That's an assumption. Willard F. Libby introduced radiocarbon dating in 1940 and got the Nobel Prize for it in 1960. Libby assumed that the amount of atmospheric radiocarbon was at equilibrium, was constant, because he said...
Give me Euler's number to 25 digits.
What's that? I'm sorry, what'd you say? Okay. Radiocarbon then Libby assumed that the amount of atmospheric radiocarbon was at equilibrium and it was constant. And then I know it wasn't true. But it should have been at equilibrium if the atmosphere was less than 100,000 years old. And so that is a major problem for them. I don't see how they can get around it. In fact, it's a double-edged sword. It comes back and cuts them. They try to use it, but it comes back and bites them. Even if all the assumptions are true, the practical limit is about 50,000 years for a maximum age that can be obtained with radiocarbon dating. It's certainly less than 100,000. And so each 5,000 years or so, it's going to cut in half. You keep cutting in half, and after a while, you have almost nothing left. Okay. And so you can't just keep going with it. That becomes ludicrous. There's also a limit on the amount of material to be tested. What we have is the material being dated must be organic material as well. It's dating organic material is what it's doing. Now, until 1977, it required about 3 grams of carbon to radiocarbon date some organic material. That's a bunch of carbon. 3 grams is a whole bunch of carbon. They had to take a big log and burn it up and get 3 grams of carbon out of it to figure out how old it was. Since 1977, however, with the development of accelerator mass spectrometry, organic material can be radiocarbon dated with a milligram of carbon. Well, that's a whole bunch less, isn't it? That's a whole milligram is 1,000th of a gram. So go from 3,000 grams, 3,000 milligrams to 1 milligram. So it's by a factor of 3,000 to 1, it's been reduced. So they can take smaller amounts of material. If they're going to date some object by it, they had to actually burn the object up and destroy it. That's what they had to do. And they were not really wanting to do that very much with old objects that they had. If the dating is from charcoal and burned in a home or a campsite, there's no certainty that the wood that was burned was not old wood that had laid in the place for many years. They don't know how long the wood had laid around before it was burnt, right? Drier, cold climates, wood may lay on the ground without decomposing and be hundreds of years old when it's used for fuel. That'd give an incorrect date to it. It's likely that there was large amounts of wood in some of the colder climate regions of the Earth at the end of the flood. Now, if there was no radiocarbon in that wood, then it would that certainly would not have any radiocarbon, appear to be quite old. And if our model of the flood is correct, there wouldn't be any in it, or almost none, and it would appear very, very old from the radiocarbon dating. Ashes from fires where the wood was used would appear to be thousands of years older for radiocarbon dating than its actual age. Okay. Now, water vapor canopy also would prevent ozone from forming. Ozone is produced when the diatomic, now di is two atoms to a molecule, oxygen molecule, that'd be O2, is separated into 2 separate oxygen atoms, O. And then what happens is the 2 oxygen atoms join with 2 oxygen molecules, O2, they form ozone, and that will be one with 2 ozone molecules, O3, ozone. Okay, O3 molecules, ozone. Now, ozone is used, it does protect us some from ultraviolet radiation. Oxygen is the most abundant element in the Earth's crust. Now, Malone tells us it exists primarily as O2, that's what we breathe in the air, but another important and life-saving allotrope of oxygen is ozone, is O3 is present in the upper atmosphere, the stratosphere. And let's go back. The allotrope, if you that have had Greek, is from allos, and so it's like it. It's the same, it's made out of the same material, but it's still made out of oxygen, see? So we have two allotropes of oxygen, O2 and O3. O2 and O3 are two allotropes. Now, there in the stratosphere, it absorbs the powerful ultraviolet rays from the sun that would otherwise penetrate the surface and damage living organisms. So it blocks out some of your ultraviolet light from damaging us, okay? And they got pretty excited about it several years ago to do away with some of the refrigerants in some of the air conditioning systems, okay? And it just happened to be about the time that the patent went out for the company that owned the patent on that refrigerant. Did you know that? Okay, interestingly enough. Okay. An allotrope is two or more, I got off the subject, I'm sorry. An allotrope is two or more molecular forms of the same element. Like here we have O2 and O3, oxygen, normal oxygen, molecules O2 and O3, all right, called ozone. Sarah, now then, I'm arguing here based on the Bible. Now, Sarah was the half-sister of Abraham, Genesis 20, verse 12. And of course, the atheists may make a big deal out of this, but you see, if you start with two people, they've got to inbreed. They've got to marry one another. And if they're mutated like crazy, they just go downhill right quick. In fact, the fact that they could marry and not have mutations proves they weren't mutated, okay? They didn't have many mutations. So she was a half-sister of Abraham, yet apparently Isaac had no adverse mental or physical effects as a result of such a union. Why? Well, right here in Genesis 20:12, we'll get to it in a minute. Moreover, she is indeed my sister, the daughter of my father, but not the daughter of my mother. And she became my wife. So Sarah is this, you got the same father, but different brothers, okay? And we call those half-sister brother, half-brother and half-sister. Abraham lived in Genesis 25:7 to be 175 years old. Isaac lived to be 180. His son outlived him. Genesis 35:28. Therefore, he wasn't highly mutated, okay? It hadn't been fully manifested yet. And of course, if you start with 8 people, and there's no evidence that Noah and his wife had more children after the flood, it's possible they did, but I don't think there's any evidence whatsoever that they had any more children. I think the scriptures tell us that all of the earth was populated by the descendants of Ham, Shem, and Japheth and their wives. And so you had to marry a cousin at the very best. And so everybody was from the same, they were same genetically out of these 6 people. Ham, Shem, Japheth, and their wives. Each of them had a wife. And these are the days of the years of Abraham's life when he lived 15 years, that's 175 years. The days of Isaac were 104 score. A score is 20, so that'd be 180 years. Okay. So he outlived his father, so he wasn't, I would argue, he wasn't mutated. Now, there's some evidence that there was not an ozone layer before the flood. I think the ozone layer had to build up after the flood. Chemically, water vapor is the primary source for the hydroxyl radical in the in the atmosphere. Recent work has shown that water vapor concentration determines the effectiveness of heterogeneous reactions. Now, you that have studied Greek with us, heteros is the two things of a different nature. See, this is from the generation or beginning reactions that destroy ozone in the lower stratosphere. So water vapor destroys ozone, and increase in water vapor would thus lead to greater ozone loss. Now, they're worried about that, but they're not even looking at the fact that ozone itself would protect you from that ultraviolet radiation as well. Heterogeneous is consisting of dissimilar or diverse ingredients or constituents. Okay. They're ruling that out. He was worried about Oltmann and Hoffman were. Water vapor would not destroy the ozone layer without the presence of halogen gases. There had to be halogen gases there for it to happen. Any of the 5 elements, chlorine, fluorine, bromine, and bromine, and iodine, astatine, and these 5 elements are halogen gases. The destruction of the ozone layer by halogen gas is discussed further in chapter 10 of my book. We'll come back to it later. Okay, get back to it at a later time. Right. Now, ozone dissipates a wide range of the ultraviolet spectrum. Ultraviolet light is also absorbed by water vapor. Now we're going to look at water vapor now. Summarizing these absorption data, important absorption by water vapor extends upward to 1900 to 2000 angstrom units. A with a zero on top of it is angstrom units. Now, a symbol here is the abbreviation for angstrom unit. 1 angstrom unit is 1 times 10 to the minus 10th meters. That would be 1 divided by a 1 with 10 zeros following it. So take the number 1 divided by 1 with 10 zeros after it, and that would be an angstrom unit. That's how many meters an angstrom unit would be. That's the small unit. We're down to the width of atoms and stuff like that. That's what we're down to, pretty close to stuff like that. It's very, very tiny distances, okay? With the absorption of ultraviolet light by large amounts of water vapor, there would not be a need of a large amount of ozone to protect organisms because the ultraviolet light was being already blocked out by the oxygen, by the water vapor canopy. So it would stop it. We wouldn't need it. And according to Berkner and Marshall, 10 meters of water, 32.8 feet of water, would absorb all the harmful ultraviolet radiation. Now, I chose this number because this is a magic number here for us. 32.8 feet or 32 feet is about, if you went down 32 feet down under in a pool, in a body of water, you would have double the pressure on your body. That would be double the barometric pressure. If you had 10 meters of water vapor equivalent, you would have double the barometric pressure. Now we theorized at least twice, maybe 3 times the barometric pressure. So if we had 3 times the barometric pressure, we'd have 64 feet, have 20 meters. But Berkner and Marshall claimed 10 meters would absorb all the harmful ultraviolet radiation. If we had 20 meters, we'd sure enough absorb all the harmful ultraviolet. We wouldn't have any ultraviolet radiation to mutate us. UV light can mutate us as well as carbon-14 can mutate us. Questions or comments? What I'm developing here now is this water vapor canopy would protect us from mutations. That is, antediluvian men, pre-flood men would not be mutated. Okay. According to Black, and again, all of this is in my book, these references are, this will be in chapter 6. 1 meter, or 3.28 feet of water will absorb 95% of the gamma radiation. Now that's pretty hairy stuff. Gamma radiation will kill you. That's way above the top of it's at the upper ultraviolet radiation, it turns into X-rays. And then above X-rays, it turns into gamma rays. That's really high energy stuff. It kills you. Okay? And it'll absorb 95% of it, just 1 meter of water will. And with an energy level of 1.5 million electron volts, that's a measure of energy. But of course, we're talking more than a meter. We're talking about what we theorize, 10 meters, and probably close to 20 meters. And so it's going to absorb even gamma radiation. Won't get through it. All right. Any questions? The equivalent of 32 feet should absorb all harmful radiation of all sorts, even gamma radiation. All right. Mountain ranges create situations where wind currents would tend to mix the air and prevent the formation of an extensive water vapor canopy. In other words, we can't get this canopy again. It won't form again. That's what I'm trying to show now. Nevertheless, it seems likely that the uplift of a feature as large and as high as the Tibetan Plateau, that's in Tibet, the Himalaya Mountains, and the 2,500 kilometer long Himalayan mountains would have had a profound effect on global circulation, climate, and erosion, and so forth. mountain ranges will block the flow of air. The uplift of Tibet would have disrupted the west to east airflow across the northern hemisphere, initiated the monsoon-driven wind systems across India, and increased precipitation along the Himalaya. With higher chemical erosion rates cause a drawdown of atmospheric carbon dioxide, resulting in global cooling. In other words, they're talking about how mountain ranges would affect things. My flood model says there weren't mountain ranges before the flood. They came about during the flood. These mountain ranges now we're sowing will affect the climate, and they will keep this situation from going back to what we had before the flood. It won't go back to it. Mountain ranges and other factors will affect it. Volcanic eruptions send large amounts of dust, chemicals, etc. into the stratosphere. This tends to prevent the formation of a new canopy because they'll make it rain out. It'll pull the water vapor out of the atmosphere. May put some in, but the dust there will break when it must come out. Volcanoes are discussed more thoroughly, extensively in Chapter 9. We'll give it to them later. Ice caps added near the geographic poles of the Earth prevent the formation of a post-diluvian water vapor canopy. They would also be factors in this. We'll be those later as well. The flood model developed in this study does not have any antediluvian ice caps for the Earth. I'm arguing there were no ice caps before the flood. All right. This ice creates dense cold air, which moves toward the equator and moves under the less dense, warmer air and causes strong wind currents. All right. Wind lifts dust particles from wind erosion of the soil into the upper atmosphere. These particles also prevent the formation of excessive water vapor canopy. We have just a bunch of things that'll keep it from forming a new canopy. It can't happen again. Won't go back to what it was. Can't happen. Oxygen that we need to put up there is stored in the carbonates, the limestone and so forth, oxides. Oklahoma, where I live, has a lot of red soil. That's iron oxide. It's iron. It's rusty. It's rusty iron. That's what it is, and which means it's iron with oxygen in it. So a lot of oxygen in that soil on the crust of the Earth here. There's crust contains the equivalent of 63 bars of carbon dioxide, according to Hunton. Now, one bar is at 1 atmosphere. It's a normal atmospheric pressure. That'd be 53 times the atmospheric pressure we have. Considerably more than enough oxygen to give 35 to 40% postulated by this author. I think the oxygen in the atmosphere is probably between 35 and 40%. We've already set that forth. So this is all documented, see, in scientific journals, okay? The oxygen, therefore, is just not available to put up in the atmosphere. We can't get back to a 35% or 37, 38% oxygen in the atmosphere because it's in the rocks, it's in the soil, it's just not available. Carbon dioxide would lose its carbon to the abundant number of plants in the antediluvian environment, giving large amounts of oxygen, O2. So before the flood, the plants were cycling carbon out of the atmosphere from carbon dioxide and putting out O2, which would be oxygen that we breathe, that we need. And I believe God created the whole forest when he created it. He didn't just create one tree and then it reproduced. The whole forest was set in place, in situ, in place. In the antediluvian canopy, this oxygen was compressed by the water vapor, which was in the upper atmosphere. Right? With this oxygen stored in the Earth's crust, it cannot go back can't form a water vapor canopy. Just can't form it. Again, everything's working against it. Don't expect it to ever go back to what it was. God saw to that. Organic matter buried in the sediment laid down by the flood limits the amount of oxygen in the post-diluvian atmosphere. Organic matter stored some of it as well. This is in addition to the oxygen that is present in the carbonate rocks and is in the oxides, iron oxide, like in Oklahoma, we got a lot of red soil, copper oxide, and so forth that are in the crust of the Earth. And so we have various metals that will oxidize, copper and iron and so forth. We call iron oxide, we call it rust in the United States. That's our word for it. Oxygen gas, Werner and Canfield tell us, O2 is present in today's atmosphere's concentration of 20.9%. I call it roughly 21%. The most important long-term process affecting concentration are O2 production by the barrel of organic matter and sediments. So he's telling us the most important process that affected how much oxygen we have in the atmosphere is the barrel of organic matter. That's what Bernard Canfield claimed. All that organic matter changed it because these fellows say it was 35% in the past, but a bunch of organic matter got buried and then we lost it in our atmosphere and it doesn't have as much oxygen as it did. That's what they're claiming. Photosynthesis, sunlight comes down and a plant then takes in oxygen, takes in sunlight and oxygen and carbon dioxide, and it takes in carbon dioxide and sunlight and water, and then makes a plant, and it puts out oxygen, O2. We breathe it in. So we get double benefit from the plants. We get oxygen that we breathe, and we get food that we eat from them. And sometimes we get something pretty to look at, like flowers, okay? Any questions? All right. We have what's called the Calvin cycle. We won't discuss it in great detail, but this is the process by which plants produce their stems and their leaves and all of that. This is your whole process here, set forth as the Calvin cycle, okay? Now, the Postdiluvian atmosphere and biosphere, and that bios is life, interact and produce a condition which prevents formation of another canopy. So we have another situation that affects it. Now, we just got all these things that keep it from happening again. These interactions are called biochemical feedbacks. Let's look at them very quickly. Perhaps the strongest and most direct means by which organisms affect climate is through their control of the composition of the atmosphere. This, again, is from a scientific journal. The concentration of carbon dioxide in the atmosphere is determined by a complex set of processes, but a key process is the uptake of carbon dioxide by plants in the surface of ocean and on land. The primary source of condensation nuclei for cloud droplets over the oceans is production of sulfurous gases such as dimethyl sulfide by tiny organisms in the surface waters. Now think about this. This gas, dimethyl sulfide, is produced by tiny organisms in the oceans, in the surface of the oceans. In the atmosphere, these sulfur-bearing gases are converted into sulfuric acid particles, right? H2SO4, sulfuric acid, which form the nuclei around which cloud droplets form by condensation for water vapor. What makes clouds? They concentrate on sulfuric acid particles. And sulfur-bearing gases do this. Now, what produces them? There are organisms tiny organisms in the surface waters. Now, we've already talked about the effect, the pasture effect. If the barometric pressure changes, these organisms could very easily have not produced this dimethyl sulfide because it appears to be being produced as a result of having being anaerobic. And so we get a situation here where we wouldn't have these produced. The antediluvian barometric pressure exceeded the pasture point so that these organisms did not produce sulfur-bearing gases. It give another reason why we had no antediluvian rainfall. We have to have these to have the rainfall. If we don't have them produced, there won't be any rainfall. That would explain no rainfall. It's not limited to marine and aquatic environments either. Let me point that out. Okay. On the continents, the breakdown of organosulfur compounds during fermentation. Okay, fermentation. Well, that's what Pasteur found with his Pasteur point. Oh, see, it's fermenting. This organic sulfur organosulfur compounds are produced through fermentation. Fermentative decomposition of organic matter is probably the most important mechanism for the release of sulfur volatiles. So it's all due to fermentation, which won't occur if you have a high oxygen atmosphere and a higher barometric pressure. So we won't have any rain. That's why we didn't have rain. Due to the difficulty of obtaining representative data from land biomass, the magnitude of this flux is still poorly known. Now, what we're saying is, he's saying biomass, like a pile of leaves out under the forest, they will decompose and produce some of these gases. And that's what he's saying. And that makes it rain more, okay? Because it's particles on which we can have cloud condensation nuclei, they're called. We can have cloud droplets. This will also explain why there's post-Diluvian rainfall, but one reason why the water vapor canopy cannot form again, because it won't let it accumulate. It just keeps making them into clouds. So as they go up, they turn into clouds because of this sulfur gases. This would also help to explain the absence of antediluvian rainfall, before the flood. All right. Production of sulfurous gases, Hartman, page 250, changes the albedo of the Earth. Now, that's the reflectivity of the Earth, the ratio of reflected light to total light coming in. If we have half the light reflected, the albedo is 0.5. If we have 60% of it, it's 0.6. It's the ratio of the reflected light to the total light coming in. Any changes in the albedo of the Earth will affect the temperature of the Earth. If you reflect more light back out into space, it cools off. If you don't reflect as much back out into space, it warms up. So the temperature of the Earth will be affected by the albedo as well. This is a complex system, very complex. Any changes in the albedo of the Earth will affect the temperature of the Earth and the amount of water vapor being generated by the evaporation. If you cool it off, you don't generate as much. Okay. Clouds of liquid water droplets form only in the presence of CC and cloud condensation nuclei, changing the size distribution or concentration of the CC and cloud condensation nuclei, cause the size distribution of cloud droplets to change, which could affect the coalescence and rain production process, possibly the time average cloud cover. This gets into some biology, but physics of it. However, the effect would be well established, that which we think to be the most significant effect, is that changing the size distribution of droplets would change the reflectance, the albedo of the clouds. In other words, it will reflect more light back. Clouds reflect light back. This leads to a decrease in mean radius of the cloud of the droplets, which causes an increase in total surface area of droplets in the cloud, thus an increase in cloud albedo. So it depends on the size of the droplets as to how much is reflected. That's what he's telling you. Cloud droplets. And again, all of this is complicated. There's a bunch here. Clear sky albedo, what it looks like. Right there, total sky albedo, there's a whole bunch of reflection due to clouds. And so we get less reflected here with this clear sky and more reflected with the albedo for clouds. Reflects more back out into space. Content of water vapor in the atmosphere is limited by condensation and precipitation. Below the supercooling temperature limit, minus 40 degrees Celsius, above about 10 kilometers. That's also minus 40 degrees Fahrenheit. That's where they're equal, incidentally. That's typically a question sometimes in physics or chemistry courses, just to trick the students. Minus 40, minus 70, minus 40 Fahrenheit equals minus 40 Celsius. That's where the two axes, the graphs cross one another. That's the one point where they cross. The content of water vapor diminishes rapidly as it goes up. The colder it gets, the less water vapor it's going to have. And the well-known stratospheric cold trap prevents significant effective circulation of water vapor upward above about 10 kilometers. So it kept putting up higher because it's too cold. And that's another factor. Once it cooled off, it's not going to warm it back up. There's a limit. Prior to the flood, the water vapor canopy would absorb all the energy in both the infrared and ultraviolet spectrums, will elevate the temperature of the water vapor. So it would allow it to have more water vapor up in the upper canopy. The elevated temperature of the water vapor would move the cold trap above the 10-kilometer level and allow more water vapor to be stored in the atmosphere because the temperature would be higher. And this minus 40 degrees is pretty cold temperature, 40 degrees Celsius and 40 degrees Fahrenheit. From the biblical and extra biblical evidence, it is evident that the waters above the firmament where a water vapor canopy was possibly supported a canopy of ozone, could have, but not necessarily. This canopy was lost during the flood because the post-Diluvian condition will probably not reoccur. I think it was God's intent that it never come back again. So he set things up so it will not come back. This canopy was the source of the 40 days of rainfall during the flood of Genesis 6 through 9. This helps to explain a number of matters, such as the longevity of both mankind and animals. We've already seen how they wouldn't be mutated. The large size of some of the antediluvian animals, if they live a long time, we'll see that later. The absence of rainfall before the flood, and it makes reliable radiocarbon dating of antediluvian organisms impossible. Can't be done. All right. Now, let me point out, and then the class is yours. If we look at animals, some animals keep growing all their lives. Most mammals reach a maturity and they cease to grow. Now, you take reptiles, all your reptiles, they'll keep growing all their lives. So if you take a lizard and let him grow to be 1,000 years old, he'll be real big. And so this explains some of your dinosaurs being quite large, and I think we still have them today. Some of them, a lot of them still are with us. They're just smaller varieties of them. All right, that's the end of our class for today. It took about an hour, which is what I thought we'd do. I went a little fast with it, but do you have questions before I get off? Anybody? All right.